Hello everyone, welcome back. So in this lecture we will be discussing the optimization strategy for the loss function that we have defined for variational autoencoders. So as you may recall that our main target is to find the optimal values of theta star and phi star, which are the weights and biases of the generator and recognition model that we have defined earlier. So that is represented in terms of the optimization framework as argument that minimizes this loss function. That's why we write it as argmin. So the argument that minimizes this loss function L theta comma phi over this theta comma phi. So whatever value that minimizes this argument will be our optimal values of theta star and phi star. So in variational Bayesian method, this loss function, the loss function that we have defined over here, is also known as variational lower bound or evidence lower bound, that is elbow. This lower bound part comes from the fact that the KL divergence is always non-negative. Thus L theta comma phi is the lower bound of log of P theta x. So for the proof of this statement, let's recall our earlier derivation that we have done for the loss function, which is repeated over here. So this is easy because in the last lecture we have already derived it, and also you know the property of the KL divergence that it has to be greater than 0. So once you fit this inequality into this one, you will obtain this result. So what this result shows is that you are minimizing the loss, so we are maximizing the lower bound of the probability of the generating real data samples. So that's why L theta comma phi r is the lower bound for this probability function. One important thing that has to be kept in mind during the optimization of these parameters theta star and phi is the derivative involved in doing so. What I mean by this is, so let's say if you are optimizing theta star and phi star as argmin of theta comma phi, where loss is the function of theta comma phi. So what you will do is you will follow the alternate optimization principle, in which what you will do is you will do optimization of the theta star first by fixing phi constant, and in that case you will do the derivative with respect to theta for this particular function, but in this case your phi will be a constant. So whatever value of this theta star comes out from this result will be fed into the another optimization scheme in which you are finding the optimal value of phi. In that case you will do the derivative with respect to phi in this framework, but the value of theta that you will put in this loss function will come from this. You will put the value of theta star into this loss function, and once you obtain the value of phi star, you have to again go back to this optimization, and then you will put the value of phi star over here and then calculate the value of theta double star, and then again you have to calculate the value of phi double star by putting the value of theta double star, and this cycle will keep on repeating for fixed number of iterations, that is it can be from 1 to 10. So then you will obtain the optimal values of theta and phi. So this is the principle behind the optimization strategy that we have to carry out for obtaining the optimal values of theta and phi. So while doing this derivation, what researchers have found is there is no problem when we are doing derivative with respect to theta, but during this process where we are doing the derivative with respect to phi, the problem occurs, and we will see what that problem is and what is its solution. So the solution I will tell you here is that this problem is solved through reparametrization trick, which we will discuss in this lecture. So as you can recall our earlier derivation for the loss function, which is defined over here. So what we will do is we will find the optimal value of theta and phi by taking derivative with respect to theta and with respect to phi. So the optimization is carried out with respect to both theta and phi to learn these PDFs, that is q phi of z given x and p of theta x given z at the same time. So we will be doing optimization strategy on both of this. So this is the optimization framework. So what we will do is we will run the algorithm for fixed number of iterations, that is up to n, and so in that iterations the very first step is to calculate a derivative with respect to theta, and the result will give you the optimal value of theta over here, and so this is the expression for it. So you are taking the derivative with respect to theta. So let's do that. So you can see that The second term, which is over here, is independent of theta, so its value will be 0. And this theta can easily move inside the expectation operator. So that's why we are writing it as del of theta log of p theta x of z given L. Please note that z given L is basically the samples of ZL coming from this probability density function, that is q phi of z given x. And this summation is coming due to the Monte Carlo estimate for the expectation operator. So we remove the expectation operator and put this average summation to get the approximate value of theta I star. So once we obtain the value of theta I star, what is our next step? Our next step is to calculate the optimal value of phi I star. So we will do what? We will differentiate with respect to phi for this loss function, and what we will do? We will take the optimal value of theta I star into this loss function, and then we will calculate the optimal value of phi I star, phi I hat. So let's do that. So this is what we are doing in the next step. We are doing the derivative with respect to phi. But now you see here there is a problem, and the problem is that for this term it is okay, but for this term there is a problem, and the problem is that the derivative delta phi is harder to estimate because phi appears in the distribution with respect to which the expectation is taken. So phi is actually appearing in this distribution here. Expectation is taken onto that distribution. That's why it's difficult to take the derivative with respect to phi. So you can see that this identity is not valid. That is, if the expectation is taken over the distribution which is dependent on phi, you cannot pass the delta phi inside this expectation operator. As you can see over here, it's an inequality sign, so you cannot do this type of activity. So as a result of which, how to solve this problem? So if we can somehow rewrite this expectation in such a way that phi appears inside the expectation, then we can push the gradient inside the expectation. That is, if we can move this phi, which is over here, inside the expectation. Inside the expectation means inside this box. Then we can somehow take the delta of phi inside this box. So we can move this phi inside this box by using this type of transformation. That is, it's a linear transformation which depends on epsilon naught and x, with epsilon naught sampling from 0, 1. Once we do this, we are taking expectation over to the random variable epsilon naught, which is sampled from this Gaussian having 0 mean and unit variance. And you can now see that the phi has been moved from this position to inside the argument. And for our case, we are using the linear transformation of mu of phi x plus epsilon naught times this as the function. So g phi of epsilon naught x, which is also z, is taken as mu x plus epsilon naught times sigma of half of the random variable x. So this is the transformation that we are trying to use in order to do this parametrization trick. And here z is also basically, it's a Gaussian of having mean, mu and sigma. So by writing this transformation, we means that we can obtain this Gaussian of any mean and sigma from 0, 1 using this transformation. This is very standard transformation that can be found in any probability course, where you are transforming a 0, 1 Gaussian function into a Gaussian function having any mean and covariance. So by using this, we are performing this trick, which is this one. Instead of sampling z from this q5 function, which was earlier the case, that is here, what we are doing is we are sampling from a Gaussian random variable of 0 mean and unit variance, that is epsilon naught is sampled from this. Then we are linearly transforming this to obtain z by using this linear transformation over the epsilon naught, so that the transformation will be realizing this random variable, this Gaussian random variable having arbitrary mean and covariance sigma. So this is just another way of saying what I have just said here. So what is this process now? So this is basically a reparametrization technique where you have shifted this problematic node to this part of the argument. So by visualizing it graphically, you can see over here that in the original form over here, this node was the stochastic node. By saying that it's a stochastic node means you are sampling z from q of phi z given x, and phi was happening in the distribution over which the expectation was taken. So it's a stochastic node. So in the reparametrization form, which we have done through this transformation, what we have done is we have pushed this stochastic node outside. By pushing it outside means now we are sampling epsilon naught from n0, 1, which is from outside. Then we are doing the linear transformation g phi of x, which we are defining over here, to make the behavior over here in the similar way as that it was in earlier case. By moving the stochastic node outside means then it is easy to backpropagate along the phi. In earlier case, because of the stochastic node, the backpropagation of along the phi was not possible. So that is the same thing I am explaining in this graph. And here when we are doing the backpropagation, we are putting out the stochastic node outside and we are sampling it through a Gaussian random variable having zero mean and unit variance, and then we are feeding this using this linear transformation which implements z. So it's very easy to now backprop with respect to phi as the stochastic node is moved outside this computational graph. So in terms of mathematics, we are just repeating here the same statement that we started with, that is, it is difficult to carry out the derivative with respect to phi because the expectation is taken over to the distribution which is dependent on phi. So what we are doing through the reparametrization technique is we have removed this phi from this argument and moved it inside. And this is basically the random variable which is taking the samples from 0, 1, whereas ZL is basically the samples that we are obtaining from this probability density function, that is P epsilon naught. So now once this transformation is done and now you can see that no phi is appearing here, then what you can do is you can easily move this delta phi operator inside the expectation operator. So that is what we have done over here. So we have moved the delta phi inside the expectation operator, and the ZL is sampling values from this P epsilon naught. We have to calculate the derivative with respect to phi for this second argument also, because this second argument also depends on phi. So now the first argument over here can be easily represented in this form. This is already discussed. This is basically the Monte Carlo estimate of the expectation operator, and this will still be there. And this sample ZL will actually come from this transformation where the random variable epsilon naught is being sampled from this normal distribution having zero mean and unit variance. So let's conclude this lecture by saying that the reparametrization trick is because of the reason of the inability of taking delta phi with respect to the loss function. That is why we are using the reparametrization trick to avoid this situation. In the next lecture, we will implement the variational autoencoders in Google Colab. Thanks for watching my lecture. See you next time.